Hello everyone. So in the last video we talked about how indexing works and we talked about different types of indexing like primary indexing, clustering indexing and two types of secondary indexing. So and we saw that how indexing can help us reduce the number of block access to search a data item in the database. But so that works fine, but let's take a scenario where our database is too large. For example, let's suppose our database has 1,000 records. So if we go with that previous example where there were we were storing roll number, name, and age of the students, then if there are 1,000 records or 1,000 student information, then it would take around 500 disk blocks, right? It would require 500 blocks, as one block can store two students data or two records, given key, let's suppose the block size was 120 bytes block size. Now when we create an index of 500 blocks, what will happen? It will be, let's suppose we are creating the primary indexing only, so our index file will have at least roll number and block pointers. So, and for example, roll number 1 has the block 1, roll number 3 will have block 2, as it like this, and there will be how many records will be there. It will be for 999 will have block 500, so there will be 500 entries in the index also. And to store an index file which has a 500 entries, will take quite a lot of space, right, in the disk itself. So for example, if we are saying ki, as we know ki roll number takes 4 bytes of information, and let's say block pointer takes 16 bytes of information, so one index entry, how much space this one entry of index will take? 20 bytes, right? And to store this index file which has 500 entries, how many blocks are needed? So let's suppose कि in one block number of entries in one block, how many there? 120 divided by 20, which will be 6 index entries in one block. So if we have to calculate for 500 entries, we'll need number of blocks will be 500 divided by 6, which will roughly come around 84, right? So now that is a large block numbers, right? Let's suppose you wanted to search something in the index to, right, for example, let's suppose you are searching for roll number 598. So in the worst case, if we apply linear search on the block, we need to search for 84 blocks. And if we are trying to access 84 blocks or 84 that means 84 disk access, which can be quite slow. So how can we improve this performance given index is too large? How can we improve our search in the index? So for that purpose, what we do, we store indexing in a tree format. So in the data structures, you must have studied about tree data structures like binary trees or BSTs, binary search trees. So what we'll do, we'll use a tree data structure and store our index in a form of tree, so that our search time in the index becomes smaller, and we can and we are required to less disk access for the searching. So and the trees we are gonna use in this DBMS are two trees, B tree and B plus trees. Okay, so let's talk about B tree first and how it works, and then we'll talk about the B plus tree. So B trees. So how does B tree work? So whenever we talk about B tree and B plus tree, we talk about key it has a order. Let's suppose it's a order P B tree. So what does this order means? Order means ki how many children a node can have. So this is technically maximum number of children a tree node can have. That's what we mean by order of a tree. Now in B tree, a node can have more, like in binary tree a node can have at max 2 children, but in case of B tree, that is not restricted to 2 only. A node can have any number of children. So the number maximum children a node can have is denoted by this P, or order of the tree. And so, and what else are there? And the search keys on which we want to search. So a node will have some search keys and some tree pointers. So a B tree node will have three things. What are these three things? First, it will have keys on which we want to search. Second, it will have the record pointer. What is this record pointer? This record pointer points to the disk block where that key is stored, where data of that key is stored. So there is one record pointer for each key, and it will point to the actual disk block where that data is stored. For example, let's say in case of our, if there is a key 2, it will point to the block B1 where the 2 is stored. Similarly, key 4, it will point to the block B2 where 4 is stored. Okay, so the record pointer in each node of a B tree will point to the original disk block where that data regarding that key is stored. So that's why it becomes easier for us to just search for the key in the tree, and from there we can find the original disk block where the data is stored, and we can just directly refer to that or directly retrieve the data from. And the third thing that a tree node will store is tree pointer. What is tree pointer? This will point to the child node of the tree, child node of that particular node. Okay. Now, before we continue our discussion on B tree, first you need to understand that these trees are itself stored in a hard disk. So when this record pointer points to a block where disk block where the actual data is stored, and the tree pointer also points to disk block where next pointer or next node is stored. Okay, so for example, this node is one disk block, right? The other children are another disk blocks where other keys are stored, and something like this. So each node will have some children, and they are on itself a disk block. So everything is stored in a disk, and the root node is there. We first access the root node, bring it to the memory, then we do the subsequent search according to which key we want. Key is larger, greater, and okay. So the concept of searching is similar to the binary search trees, but only difference between the B tree and binary search tree is the it can have more than one key and more than two tree pointers. Okay, so there are some things we need to remember for an order B tree. For an order P B tree, there are a few things that you need to remember always. First, a node can have at max p tree pointers. That means a node can have at max p childs. Okay, so this p or the order of node tree sets a higher ceiling on the key, how many children can a node have. Second, so if there are like p children it can have, then how many keys it can have, because there, for example, there is key 1, key 2 and key 3, then there can be only 4 childs. So if there are at max p tree pointers, then a node can have at max p minus 1 keys. Okay, so that is one more thing you need to remember. Also in B tree, one condition of there is a condition on minimum number of keys also. Okay, a node should have at least p by 2 minus 1 keys. So a node should have at least ceiling of p by 2 minus 1 keys except root. So a node, so this condition is true except root. The root is exception for this condition, but except root, all other nodes should have at least p by 2 minus 1 keys. Okay, the root can have 1, 2, any number of keys. The maximum wala is true for all nodes including root, but the minimum criteria can be different for root. Root might not satisfy this minimum criteria of p by 2 minus 1 keys. Okay, so these are and the fourth property is all leaf nodes are on same level. So in bin tree, all the leaf nodes are on the same level of tree. How does this happen? We'll see an example, but you need to understand these three properties. A node can have at max p tree pointers, can have at max p minus 1 keys, and at least p by 2 minus 1 keys need to have a node need to have at least p by 2 minus 1 keys. This is not true, like this can be an exception for root itself, where root might have less than p by 2 minus 1 keys, but all except root, all other nodes should follow this property. Okay, so let's see an example. So let me create an B tree which has, for example, so if I have to give you an example of B tree, so it will be something like this. So there is this something like this, where this is your root and these are leaf nodes. Okay, so this can be like order 2 B tree. Okay, now how does operations like insertion, deletion happen in B tree? So let's see that with an example. So let's talk about insertion in B tree. So we'll understand insertion with an example. So let's suppose we have a order 3 B tree. Okay, so if the order is 3, then we need to find out कि maximum keys कितनी हो सकते हैं. The maximum keys a node can have is 2 p minus 1, right? So this is your p, and minimum keys a node can have are 3 by 2 minus 1, which is 1. Okay, so a node need to have at least minimum 1 key. And so now let's try to do some insertions. So let's suppose we want to insert following items in a B tree: 1 2 3 4 5 6 7. So we want to create a B tree of this. So we'll first insert 1. So right now there is nothing in the tree, so we'll simply create a new node having 1. Now this 1 key, what is this? Does this key stores? This node stores 3 things, right? Key, tree pointers and block pointers. So tree pointers are right now, these tree pointers are null because there is no children, but the block record pointer, which points to the actual data, will point to some disk block where this record of 1 will be stored. Okay, so this will be record pointer, and these are tree pointers in the. So I'm just showing you for you to visualize what are the information a tree node might be having. So we'll not draw all these for every node. So let's now so this is first. Now let's insert second item 2. So where will it be inserted? So insertion always happens at the leaf node. Just like binary search trees, we always insert a value or a key in that B tree at the leaf node. So we need to find appropriate leaf node using the binary search, and then we insert that item. So here there is only one leaf node, so we'll insert there only. So insert 2, so we'll insert 1 and 2. Now this is your tree where there are 2 keys, 1 and 2. Still maximum key property is satisfied, minimum key property is satisfied, so we are okay. And now let's insert 3. Again, insertion will always happen at the leaf node, so let's insert, and in the one node keys are stored in a sorted manner. So this is how we tell. But now you see that the maximum keys wala property is violated, right? Because a node can have at max 2 keys, but it is having 3 keys right now. So in this case, what will happen, we'll simply pick the middle node and split our node based on that. So what we'll do, we'll pick this one and create a new node by splitting this. So we'll simply split our split our node, and the middle node will go up, and the left part will become the left child, and the right part will become the right side. And as you can see, now the maximum and minimum wala property is again satisfied. Now let's insert one more element, 4. Where will 4 be inserted? We'll use binary search again. 2, the 4 is larger than 2, so we'll search in the right side. And 3, there is no children of 3, so we'll insert the 4 at the 3. So 1 and 3 and 4. As you can see, all the leaf nodes are again on the same level. Now let's insert one more. That's what we are inserting 5. Again we'll check 2, 5 is greater than 2, we'll go to this node and insert 2, 5 here. Three, 4, 5. Now you see the maximum key property is violated. So what we'll do, we'll simply do the split on the middle node and send the middle node above. So where will it go? It will go to the upper level node. So now the tree will look something like this. The middle node will go up 1, the left part will become the left children 3, and right part will become right children 1. So again, as you can see, all the leaves are on the same level. Now let's insert some more. 6. Where will 6 be inserted? Here we will search in the root node first. We see that 6 is greater than 4. We'll go to the right child of 4, 5. Now 5 doesn't have any children, so we'll insert 6 at the leaf node of 5. So 2, 4. Okay, and that's how it works. Now again let's insert 7, 2, 4. Now again we see that the maximum key property is violated here. So what we'll do, simply pick the middle node and send it above. So we'll do the split, and how will it will look like? It will look like 2, 4, 6, 1, 3. Left part will become left child, right part will become right child. But now again you see that this node is violating the property again, right? Because it can't have more than 2 keys, but it is having 3 keys right now. So what we'll do, we'll again split this node. So we'll again split this node and send 1, but now there is no node above it, so we'll create a new node or new root and structure our tree like this. So 4 will become the new root, and the left side of 4 will become left child of the 4, and right side will become right child of the 4, and 2 ka left side will become the 2's left side, and this right side will become 2's right side. Again this will become the iska left child, and this is how tree is created. Okay, so this looks like a binary search tree, but it is a B tree with having order 3. Okay, so that's how insertions are performed in a B tree. Now let's, so if we do one more example, maybe, okay, so let's do one more example, and after that we'll talk about the deletion part. So let's suppose we have a order 4 B tree. Okay, so and if we want to insert following values in the tree: 15, 5, 8, 22, 10, 11. So how, again, order 4 है, तो how many keys can be there? The maximum 3 keys can be there, p minus 1, right? This is p. And minimum, how many keys can be there? Minimum will be 4 by 2 minus 1. This will be 1 key only. Okay, so now let's start. So first we'll insert 15. So again, since there are no nodes, 15 can be inserted. As you can see, the root node can violate the minimum key property because the first node itself will be inserted in, right? So if it was a node order 5 B tree, then the minimum keys would have been 2. But when we are inserting the first element or splitting any element, root might end up having only one element. So the only root is the exception, which doesn't have to follow the minimum keys wala criteria. All other nodes need to follow that too. Now let's insert 5. Where will 5 be inserted? Again, we insert keys at the leaf node, so there is only one leaf node, so we'll insert 5 in here only, and it will be inserted in a sorted order. So 5 will come before 15, 15. Then again 8, so insert 8 also. It will be 5, 8 and 15. Insert 22, so let's insert 22. If we insert 22, it will become something like this: 5, 8, 15 and 22. But a node can have only 3 keys at max. Here we have 4 keys, so we need to pick up, we need to split it. So in what we are doing, we are picking middle element and splitting that based on that. But here you realize that there are 2 middle elements, this or this. So which one to pick? Now we can choose any one. We can either pick 8 or we can pick 15. So if we pick left 8, then we are saying कि right side have more child, right? If we split on 8, how will it look like? Split on 8, so it will look something like this. 8 will go up, the left child will be 5, and this will have something like this. So right child will end up having more keys, right? Or if we split on 15, it will look something like this: 5, 8 and 22. In this, left child had end up having more keys. So if left child has more keys, so then we call it as a left biasing, and if right child end up having more keys, then we call it as a right biasing. So we can choose any one. We can either go with left biasing or right biasing. only thing you need to remember is ki you need to stick with one through entire insertion. So if we continued with the right biasing, then for entire insertion, whenever there is a situation of something like this where two nodes are there in middle, you need to pick just one. You need to stick with right biasing only. You need to always split nodes in a such a manner ki tree is splitted in the right biasing form. And if we stick with left, then we always stick with left. So that's the only thing you need to remember. Okay, so now let's continue with the right biasing. And now what else I need to insert? Let's insert 10. Where will 10 be inserted? 10 will be inserted here, right? Or not? 10 is greater than 8, so it will be inserted here. So 8, 5 and 10, 15, 22. And now let's insert one more. So 8, 1, 5, 10, 15, 22. And that's how the insertion works. So if I have to insert one more element, let's suppose I inserted 20. So what happens when we insert 20? 8, the left part 1 and 5, and 10, 15, 20, 20 and 22, right? It will be inserted in sorted manner. Now again you see there are 4 keys. We need to split it, and what we did in the previous split, we continued with the right biasing. Right node should have more children, so we need to follow that same property here also. So where on which node will insert split again? On 15. So 15 will go up, and so this split will look something like this. 8, 15 will go up and become on the root. 1, 5 will stay here. 10 will come in the middle, and the right side will have 12 and 22. So since we continued with the right biasing, we need to follow that only. And if we would have done the left biasing first, then we need to continue with the left biasing itself. Okay, so that's how insertion in B tree works. Okay.